depth. And this is a diver who's taking a water bottle underwater. And he's got air in it. You can see what happens to the bottle as he goes further and further down. Let's start right about here. And there's the water bottle. He starts to get deeper. You can see it's actually crushing the water bottle. It has air in it. That's only 20 feet down. That's less than 1 atmosphere increase.
That water bottle doesn't have any water in it?
Nope. Water's not compressible.
Does it have a cap on it?
Probably so. Because otherwise water would fill in, right? And water's not compressible. But you could do it with the cap off, with water in it.
Well, that's like when we go down to the Titanic, we have to be in those
But that's what's happening to your body. It's what's happening to your lungs, right? We're crushing your lungs, making them smaller, which increases their pressure. And is that Henry's law right there?
No, that's
Boilers.
Boyle's.
Very good. Boyle's law, exactly. Right? P equals 1 over V. You guys had me scared for a second. All right. 2 things we're going to do. You're going to get a renal anatomy lecture, but we also got to do a little bit more respiration. Oh, shit. You guys are going to learn how you can kill grandma, get your inheritance, and leave no evidence behind.
Frogs. Oh, okay. All right.
Promises, promises, promises. Yeah. Okay. So, we have to talk about chronic obstructive pulmonary disorder, COPDs, and emphysema. So, what I drew for you guys is my version either of a puppy dog's paw, right, or of your alveoli. Each one of these is an alveolus. This is a normal representation of some alveolar structures. Over here, I have the version of emphysema, where I'm showing you significantly less surface area. That's important because you got to remember that surface area allows for the place of gas exchange to take place, for diffusion to take place. So with less surface area, where you're going to have less gas exchange taking place. Now, aside from my 2 individuals, anybody tell me the normal PO2 value in the blood as it leaves the lungs? What is the normal arterial PO2 value as it leaves the lungs and heads to the heart?
The 104?
Which one?
Not 40, no.
No, 104.
100?
105, no. You're close.
104.
No.
Oh.
Is it 100?
It's 100.
Yeah.
All right. You guys should know that. You've had plenty of time to get that down. All right. PO2 equals 100. What's the PCO2 value as it leaves the lungs and heads to the heart?
40.
40. Very good. Much better than the first lab group. All right. Now, I don't think you guys should know this, but due to emphysema, having less surface area, would you expect the PO2 value to be higher or lower compared to normal?
Low.
Exactly. It's because you have less surface area, right? There's less opportunity for gas exchange. What about your PCO2 levels? Higher or lower?
Higher.
Higher, exactly, because now we have less chance of getting rid of that CO2. What is that process called that happens between the lungs and the pulmonary capillaries?
The alveolus.
No? What kind of respiration is this? It's external respiration, right? You should know that by now, right? If not, you got to work on that, but it's a little clue of, okay, maybe I'm not spending quite enough time. What you are going to find out is the PO2 in emphysema patients that have chronic obstructive pulmonary disorder will be about 50 in some cases. And for some PCO2s, it'll also be 50, which makes sense. The PO2 is lower due to less gas exchange abilities, due to the loss in surface area. The CO2 is higher because of reduced external respiration abilities as well. Couldn't get rid of all that CO2 as it moves by. Nurses have a nickname for this. Does anybody know what the nickname is?
Pink puffers?
Nope. Not for this specific scenario.
Oh.
I've heard it, but I forgot it.
It's really obvious. They're called 50-50s.
Yeah.
Now, here's normal. If you had someone that had a PCO2 of 50, and you know what normal is, would you expect them to have an increase in respiration, a decrease in respiration, or no change in respiration due or compared to normal?
It decreases.
Should be what? Increase, decrease, or normal? Should be increase. Don't you have a graph that shows that CO2 increases, we get increased respiration?
Oh, yeah.
Oh, yeah. Scott, maybe you want to turn the graph right side up instead of upside down.
To my brain, right?
Right? So now here's the thing though. Alright? Notice I said, what would you expect? They don't have the appropriate increased respiration rates. Alright? So you get a lack of increased respiration rates. Now you got to figure out why you get a lack of increased respiration, because you expect them to have more because they have more CO2. So we're going to then take a little trip. We're also going to tap into your 241 memory. I heard that, Kaz.
That was Scott.
No.
Who said sweet?
Me.
We're going to see what Scott remembers then. We're going to pick on Scott. Should be long enough. And then afterwards, Dave and I can have a debate about the importance of refractory periods. Or the lack thereof. All right. What is blood mainly comprised of?
What is what comprised? Plasma.
Blood.
Water.
Plasma.
And what is plasma mainly comprised of?
Water.
Water, okay. Do we have gases in our blood?
Yeah.
Like O2, CO2, right? Okay. So, you gotta keep on, anytime you have your blood, you're always thinking of this. All right. Now, this is going to represent our cerebrospinal fluid, or CSF. We are looking at a structure in your medulla. What structure might that be if we're talking about respiration rates and the medulla? Anybody remember? Any clues?
Medulla. The chemoreceptor, the central chemoreceptor.
Oh, yeah,
And what's its AKA? What's its nickname?
CSF.
The hydrogen ion sensor. Exactly. Very good, everybody. This is going to be a chemo, well, a central. Right, chemoreceptor. Located in the medulla oblongata. Do that. And the nickname hydrogen ion sensor. We'll give it a receptor for hydrogen ions. I made that a bit too big. I mean, we'll just make it a kind of a flat cell. It doesn't have to be. We'll just do this. All right. Cerebrospinal fluid. Got a capillary running through my medulla oblongata, right adjacent to a central chemoreceptor known as a hydrogen ion sensor. What am I trying to show you here? These little bumpy things. Very good. Those are epithelial cells, right? Otherwise known as endothelium. Can CO2 have simple diffusion through that, or does it need to be transported?
Simple.
Why?
Because thin.
Nope.
It's non-polar.
That's nonpolar. Nonpolar things can pass through your lipid bilayer, right? So we got CO2 diffusing in here. Due to the lack of aquaporins, water's not going to do that. Can anything else diffuse out of the blood and go into this? Anybody else in here do simple diffusion? Can hydrogen leave the blood and go into here?
Yeah.
Yes.
I heard a no and a yeah. Here's the answer.
Can H2CO3 diffuse through them?
No, that would also be a transport mechanism. But why can't hydrogen simply diffuse out of the blood into that environment?
It's iron, it's polar.
It's polar, all right? Ions are polar, right? Is it hydrophobic or hydrophilic? It's hydrophilic, and hydrophilic things can't cross through cell membranes unless they have help, right? Facilitated diffusion. That's why when we looked at tonight, we always had those leaky channels for sodium and potassium, right? Or pumps, because those ions can't cross the cell membrane. All right, well, do you see a dilemma? Here's my hydrogen ion sensor in the medulla.
No hydrogen.
The hydrogen can't get to it, so where in the hell does the hydrogen come from?
Does the CO2 dissociate in the CSF too, like it does in the blood? Because
Yep.
there's water in there too.
Oh, well, where does CSF come from? How do we make CSF?
It comes out of the blood. The ependymal cells in the
In the
little spaces in there.
little faces. So
The
we'll give
ventricles.
Dave a rest.
Ventricles.
He's good, right? He's already answered half my future questions. What's the name of the structure that produces cerebrospinal fluid?
Choroid plexus.
Very good. What's the choroid plexus made up of? Dave?
Ependymal cells.
And
I don't remember the other thing.
capillaries.
Capillaries.
All right. Where do you find choroid plexes? Do you remember? So is it actually safe to say that the ventricles make CSF? No, that's the location that the choroid plexus makes it, right? The floor of the lateral, roof of the thirds, anterior aspect of the fourth. Oh my God, nightmares, John, quit talking like that.
In between
All right.
the third and fourth.
Let's look at a choroid plexus. So this will be a choroid plexus idea. These will be your ependymal cells. So we're going to be drawing right here. They're cuboidal-like epithelial cells. That's a little bizarre, cuboidal-like. Just get enough of them in here so we can label one. That's what this is. All right. Now, they are actually like astrocytes, running around and covering the capillaries. Sorry for the squeaks. And we'll make it big enough we can draw. So here's our capillary. And we'll just say that change colors. This will be plasma that's in here. And so the plasma, right, can come out, write the name down here again, can be filtered out of the capillary into the ependymal cell, and out comes CSF, which we know is going to be having lots and lots of water because it was made from plasma, and plasma is mainly water. So CSF is mainly water. So there's our H2O. And then you get to do your favorite equation over again, right? So now we're going to get carbonic acid, which can dissociate into bicarbonates, and your hydrogen ion. And that's the hydrogen ion that we're looking for that will stimulate your hydrogen ion sensor. It's the CO2 that had diffused into the CSF, leading to the production of hydrogen ions, and that sensor is in that same tissue right close to the capillary bed. And then when hydrogen ions are detected by the hydrogen ion sensor, that will lead to an increase in respiration rates. So you're going to go increase RR.
Is this a normal situation?
So you're doing right now.
Okay. This is not a COPD.
Because remember, I think we mentioned the idea that your central chemoreceptor is what drives your normal, it's your primary driver for normal breathing rates. All right, now, if I hold my breath for, let's say, a minute and a half, what's going to happen to my CO2 levels in my blood?
Go up.
Everybody agree that CO2 is going to go up if you hold it? All right. If CO2 goes up in my blood, will more CO2 diffuse into my cerebrospinal fluid?
Yes.
Yeah, perfect. If I have more CO2 diffusing into the CSF, it's mainly made out of water, will I end up producing more hydrogen ions?
Yes.
Will I have more hydrogen ions to be detected by my hydrogen ion sensor? Yes. Are they breathing more? Right, because it's sensing hydrogen ions. So with an increase in hydrogen ions, I will get an increase even more so, right, of respiration rates. That's why you breathe faster when you hold your breath. If you were to really truly understand this and see this, go home tonight, sit on the bed, sit in the middle of the bed, hold your breath as long as you possibly can. And if you pass out, you land on the bed, right? But notice your breathing, or better yet, ask your partner to do it, right? And watch how fast and how deep they breathe as soon as they start to breathe again, right? That was due to the buildup of hydrogen ions in your cerebral, or in your hydrogen ion sensor tissue. And then notice how fast your breathing slows back down again, because you're getting rid of all that CO2, which means you're lowering the level of hydrogen, which means these guys are getting less sensors with them. This is what we do all the time. This is what drives your normal respiration rates. How do we know that oxygen isn't your primary driver of ventilation rates? Do you have any data that proves that? Hey, that very first graph we looked at, right? That had that kind of a long slope that kind of pulled up at a PO2 of about 60. But the other two graphs of pH and CO2 were more of a linear relationship. And for every change in CO2 or hydrogens, we had a change in ventilation rates. That shows you that this is probably more responsive than changes in O2. Now, what if I use blue? I want to use blue. Let me use green. Now let's do. Yeah, we'll use green. All right. Now, if I get elevated levels of CO2 for long periods of time, sorry for the squeeze. Try that.
Too much hydrogen.
Hypercapnia. You have to be careful how you say this. Chronically elevated levels of CO2. Not too much CO2. Chronically elevated levels. Holding your breath does not count unless you can hold your breath for multiple months at a time. Right? Chronically elevated levels of CO2 is known as hypercapnia. What's that got to do to our levels of hydrogen ions in our medulla, cerebrospinal fluid? So we're going to have chronically elevated levels of hydrogens, which does what to our pH?
Chronically low.
Chronically low. And is low pH, is that okay? Are we okay with that?
No.
Right? Because why not?
More acidic.
Acidic.
And so who cares? Well, why don't I care about being more acidic? What might be interfered with? Remember, this is interstitial fluid, and there are cells here. Cells have biochemical processes, and most biochemical processes require enzymes. How tolerant are enzymes to changes in pH?
No.
They're not, right? So you might make them a little wonky, right? So we don't want changes in pH. I have a drop in pH, that's no bueno. I need to fix that. How can I raise my pH back up again? Oh, I'm going to pick on the ependymal cells. Can't they multitask? I'm going to make two things for me. Make cerebrospinal fluid and also crank out bicarbonate ions. So they're going to be producing bicarbonates as well as CSF. Now, bicarbonate's a buffer. Here comes my bicarbonate. Going to come up and associate with that hydrogen ion. So I'm going to get my bicarbonate plus that hydrogen. What do I form? Well, you just driving the equation this way now. We're going to form carbonic acid, which can form what? CO2 and H2O. The significant thing is to notice that hydrogen that was working with that bicarbonate, right, was removed from the environment. It means that hydrogen isn't going to be sensed by the hydrogen ion sensor. The more bicarbonate, the fewer hydrogens I have to tell the hydrogen ion sensor that John is high in CO2. higher than normal levels of CO2. Not the expected respiration rates because their hydrogens are being sequestered, in a sense, by the bicarbonate due to the prolonged lowering of the pH. And that's why you don't get the respiration rates you're looking for. Does all that make sense?
Does the body also, when you have hypercapnia, so you're chronically acidic, does it increase ADH and aldosterone to get rid of the extra hydrogen ions?
So what's really nice is that if you have renal, what's called respiratory acidosis, you're going to create metabolic alkalosis. So in other words, the kidneys and the lungs will work opposite to maintain, if this is the problem of acidity, the kidneys will work to bring it back down. If this is the problem of alkalinity, the kidneys will work to bring it back up. If the kidneys are the problem for acidity, the lungs will work to make you alkaline. So they work as a tandem, which is really kind of nice.
So that would also eventually suppress this signal to breathe faster because the blood is less acidic then.
Not because the blood is less acidic, because you're still gonna get, there'll be a dampening with that, yes, but you're still gonna be pretty screwed with this idea over here. But you'll be less screwed if the kidneys weren't doing their job. Now, this is the central chemoreceptor, all right, is your primary driver of respiration rates, all right? And we look at someone with emphysema, the reason they don't have the corresponding level of respiration due to their increase in CO2 is because due to the prolonged elevated levels of CO2, which led to a prolonged reduction in their pH, let's make sure we do that. So therefore, right, decrease in pH, and then therefore fewer hydrogen ions to sensor, that I don't get the corresponding change in ventilation I would expect with your gas values. This is where I left off with the first lab group, so I can kind of keep you guys the same. On Monday, I'm going to talk about what the COPD patients will use is the peripheral chemoreceptors. I will send you guys a diagram over the weekend of the function, the mechanism of the peripheral chemoreceptors. We're going to walk through it on Monday and see how the peripherals will be the auxiliary backup regulator of your respiration rates. But to put you in that context, number one, make sure you understand this completely, so that's very well understood on Monday. And what did I tell you guys about the peripheral chemoreceptors in terms of what they're responding to?
They respond to dramatically low levels of PO2.
And do you remember maybe what an example of a dramatically low PO2 might be?
Working out a bunch.
Not so much working out a bunch. When you were all diligently studying that graph of respiration, right?
Oh, right, the low.
What did that correspond to?
40.
Really, it started at a PO2 of 60, right? Got really steep at a PO2 of 40. All right, so here we can see that that is maybe where the peripherals are kind of playing a role to increase your respiration rates, which we'll look at. And that's how we're going to kill grandma.
Or ourselves.
Not intentionally, all right? So what's going to happen in the scenario is I'm going to go visit grandma. So there's grandma in the hospital bed. She looks a little cyanotic, and I'm starving. Been a long day. It's like 2 o'clock in the afternoon. I haven't had breakfast yet. I haven't had lunch yet. So I've been chatting with Dana. Look a little purple in the lips, a little purple in the fingernails. I'm hungry. Going to go down to the Laza cafeteria. Before I go, I want to do her a little favor, so I just go over here and just turn up that O2 valve a little bit more. Think I'm helping her, and I'm going to go have lunch for about 2 or 3 hours, go on Facebook, Snapchat, Twitter, oh my God, lost track of time. 5 hours later, there's a code blue in grandma's room, and she's dead. How'd that happen?
Too much.
That's for Monday. All right, photograph this, all right? Don't give grandma more O2. Moral of the story.
Lesson learned.
I got a question. Can COPD affect like muscle mass?
I mean, it can, because you're gonna be so short of breath, you're gonna have a hard time working out, so you become a little more lethargic, and less muscle activity means more hypertrophy of the muscle, I'm sorry, atrophy, not hypertrophy, atrophy.
Well, my grandma's boyfriend, they're old. He has COPD, but his maximus and all of that, it's like missing.
You know, it might be something different with that.
Yeah.
So here's my suggestion for you folks. Take a 5-minute break, make a gear change, okay? And then come back from the 5 minutes and we're going to walk you through the renal anatomy. And then for you guys